So, last lecture we spent learning about memory management and related things. Now, today we will start a new project and take a look on how strings are represented in C and C++. This is a quite a important topic, since usually when you think about more high-level programming languages, they all have some sort of built-in string which can be used, and usually is quite flexible. With C it's not quite as simple. So let's create a project. Zack. Okay. Okay. Let's add some that includes. Yes. So the way, so first of all, as you might remember when we were talking about the different machine types, I already noted that there is no such thing like an actual string that the CPU as such could handle. For the CPU you can only have single characters, and if you want to have some sort of text, you need to construct something that leverages the CPU's features to give you the resemblance of of text. And in C and C++, the most commonly used representation for strings is a so-called C string, or it is a null terminated string. So basically it is just an array of chars, for example, char my string, and it can be initialized like you would normally expect to be able to initialize strings. You write strings as a literal within double quotation marks, and as you might remember, for single characters you use the single quotation marks. We already did this during the lectures about variables, when we used just the char data type. And such arrays of strings are with a terminating null. So what you actually get in reality, so this thing here has, as it looks, 8 elements, but in reality it will always have 9 elements. It will get an additional element and 0, which will terminate the string. So it would look in reality something like this. 2, 3, 4, 5, 6, 7, 8, 9. I might miscount it, but let's see. So space 1, 2, 3, 0. And this is what such a why is it complaining? Yes. Here we are missing the brackets that indicates an array of undefined length. In principle, when defining strings, you can also define them like this. Just need a different name for it, and it needs to be const. So the first way basically just defines an array and uses a string-like literal to pre-fill it. The array will have the size as here given. So we can int size my string size is equals is of my string. We can do that for both, and we'll see that they are show that const, so that we can see the previous. So you see it has 9 elements and the other one also 9. So there is always a 0, which gives you a few limitations. First of all, you cannot obviously use the 0 character, or rather the 0 numbered char in any of your texts. And it's important to note that 0 is not like the actual 0. So if you would want to have the printable 0, let's say we want this to be 100, then you can just use normal 0, and 0 doesn't have the value of 0. So 0, as you can see here, has the value of 48. And for example, 1 is 49, and so on, S is 116, etc., etc. but the actual 0, 0 indicates that the string ends at this point, and then there is no valid string past this point. For many use cases, this is fine. If you just work with text, you only are interested in the printable subset of all the available characters anyways. But if you work with binary data or like this, then a string is not the right type of container to hold your data. The next limitation, which here becomes immediately apparent, is that such a string is only as long as the array is plus 0. So you cannot, for example, just add two strings together. In other languages, more high-level languages, you can concatenate strings, get parts of strings easily out, append to the end of the string, etc. Here, you can do it with helper functions, but only to the length how much you have allocated space for the string. So with every string operation, you are running risk of exceeding your allocated memory and then starting to overwrite things you should not be overwriting. So and now also one thing to notice, that in these two ways of defining it, they define UA string actually slightly differently. So we could look in the assembler how these two methods differ, but in the end here you end up with an array of this size, and you can modify the array. So you can take, let's say, my string and at offset 4 insert a underscore, so replace the space with an underscore, and that will work just fine. In this case, this one is slightly different. Here what we are defining is basically a pointer, and this string that we are assigning to the pointer basically will be put somewhere in the program memory by the compiler, and we just get the address to it, meaning that it usually will end up in a read-only memory section, and we can no longer modify it. This is also why it needs to be defined as const. If we just try to define it as char, the compiler would complain that it cannot assign a defined string to a char pointer. And trying to modify it, as said, it will usually raise a access exception, since the string is not writable. Usually it's not in a writable memory location. You could of course use some special functions to make it writable, but that's not how you are supposed to do things. Okay. So we have this. Yeah. One thing that is also apparent from this sort of string is that it really doesn't have any more properties than just being this array. So let's say you would want to know how long the string is, which, you know, with strings it's quite common thing that one might want to know. But unfortunately, the way this string works is there is no easy way to know its length. The only way you can use is you have to count its length. So int my len is equal 0. Of course, there are helper functions that do this for you if you want, but just to understand how those work internally, we will implement the str_len function here manually. My str, comma, asterisk ptr is ungleich null. Strichpunkt ptr plus plus. Let's see if this makes sense. So we have our string, we advance it. No, that doesn't. Yeah, that is not needed. We can just write it like this, or is like null. Makes not really a difference. And my len plus plus. So basically, we start with a pointer pointing the first character. We check whether that is null. If it's not null, then we do this, then we do this, and then we repeat the check, and then until we reach at the end, at which point this breaks out, and then we have the string length. So here, if we put a breakpoint, we should end up with the value 9 in our mylen. So this shows you that especially, sorry, 8, since we are not counting the terminating 0. It only counts the actually used characters. So this already shows you that such a string, especially when handling larger string data like a few kilobyte or a few 100 kilobyte of text, is already really not the best thing you could do, because even a simple operation as checking the string length will need you to iterate through the whole string, which will be a huge amount of operations. As said, there are helper functions that do this for you. Is equals, but for this we need to include and include string h. And there's a function string which just takes a string and will count it down and pretty much do the very same thing we just did here manually. And in addition to this, there are quite many other helper functions. So, for example, let's create a large array. My long string. Let's give it a kilobyte of memory. Let's initialize it with nothing. Okay, and for example, if you want to assign one string to another, assuming of course that you have enough space, you can use the string copy function, strcpy. And by the way, this function is unsafe in the sense that it doesn't check whether there is actually room to copy to. It will just copy, and if the room is all, then it will keep going. It will not start. It will then keep going, and then it will overwrite things which it should not overwrite. So there is a secure version of this underscore core s, which is quite similar. But it takes also the maximal size in bytes of our string, so we can use here size of, and then as the last argument it takes the source. And with the source, again, it assumes the source is well formatted. So if you would have a situation where your source string doesn't have a terminating null, then it would start copying, and it would keep copying, and unless it runs out of space to copy it to, it would copy as long as until it reaches some invalid memory region, at which point it would crash. So there are limitations. There are quite a few functions. So for example, there are ones where you can specify how many bytes you want to copy, etc., etc. And there are also quite convenient functions that allow you to concatenate strings, but they are also, of course, internally rather inefficient. So this thing again takes destination and size. So again, those two, and we can concatenate some other string to it. Let's say 4, 5, and 6. In this case, the function will first see, well, it starts with the string, so it starts with a character, it goes through the string until it finds the terminating null, then it checks, oh, actually while it's doing it, it is checking whether it is allowed to keep going, but once it found a null, then it will start copying basically one character after the other from the source string, until the source string hits its terminating null, and then it will return. So, all quite inefficient. There is a huge amount of such helper functions defined in the strings h. When I upload this to Moodle, I will also copy in a whole comment including most of the useful functions. But just to mention, if there is like string compare to compare strings, you have functions to convert the locale, like the code page of the string. You have a few other functions which are related to memory management in this string h, like memset, which allows you to set like all the values in an array to a certain value, etc. And generally, when you are working with most simple C libraries, or most notable the Windows API, it will except for the NT DLL, all the other Windows APIs, standard Windows APIs will take normal strings, normal C-type strings instead of something more elaborate. So this is necessary to be able to handle them. You can of course also use inside your application more complex string representations. Once we switch to to C++ and then take a look on the STL library, there is a really nice class that is designed to represent a string which is simply a bit more complex. It has a counter for length. It can automatically extend its size when needed. So here, if you would cut more and more, at some point you would run out of this 1024 bytes we have allocated, and then it's the end. So usually when working with C strings, you are assembling them from something else, the way you would do it, you would first count the size, how much you know you will need, then you would allocate the memory dynamically, so you would not allocate it like here on the stack, but you would use malloc, as we have seen in the last lecture, that can be used for allocating arbitrary amounts of memory at will. And then you would copy data to that string, and this all is kind of labor intensive, to be honest. And this more modern C classes from from the C library, like the SED string, they make it really easy, because you can just make a string plus equals another string, and it will just extend the string if needed, copy the data, do all the memory management for you. And generally, when you try to use C and C++ especially in a safe way, then it is recommended to just not do your own memory management, but use all these nice helper elements, objects, which you get from the standard template library. There are also smart pointers and other means that will abstract the allocation and freeing of memory from you, which makes the whole code much more safe. A huge amount of bugs in programming come either from not allocating memory when it's needed, having too little memory allocated, freeing memory and then trying to use it, etc. And if you are using such helper objects, then those issues will not arise. For example, with arrays, as you know, I've shown this during the past lecture, that you can just write past the end of the array, and the program will just keep going until it does something that will make it crash. But for example, the STL would have a vector class where you can, which will automatically extend the memory, reallocating it as soon as more memory is required, as well as it would validate any access at a given offset, whether it falls within the range that is valid for this object. So your application would not be able to keep going and doing something unpredictable, but it will crash in a defined way, which is always preferable to it just continuing and breaking things. But well, that will come in the near future. For now, let's continue with this normal old school C strings. So one thing which is quite useful with strings is the ability to not just concatenate strings as we did here, but for example, if you can write a number to a string, or a string to a given place of a string, etc. So there is this function sprintf, and this printf, like print formatted there, mainly like just printf without s, prints it to the console, so it's outputted in such a black text box. Sprintf prints it to a string. You have also fprintf, which you can use to print things to a file. So these are quite convenient. The sprintf s option is the safe version of the normal sprintf function. It takes the buffer count, so like the maximal amount it's allowed to write, and then it takes a format string. And as you see on these 3 dots, it's a variable argument function. So the basic minimum is just this, and you can just write, let's say, test, and it will just write test to your string, which at this point is not more interesting than just the string copy or the concat. But what you can do is, since it's formatting, you can use this % and then some letter. There is a whole list of not verbose list, but at least some starter list, which I will copy in here, that will tell you which combinations mean. So %i is for an integer. We can add another string with %s. We can add a single character with %c. You can also use escape characters within this. So if you want, for example, a new line, you would make \r\n, although mostly just \n would be enough. Then you can write some auto text, and so on. And now after the comma, you need to provide all the things that you have defined in your format string. So we need an integer, so let's say 1, 2, 3. Then we need a string, so and then we want one individual character, so let's go with a exclamation mark. And now if we run it, it will copy all those things properly formatted directly into our output string. As we see here, okay, actually we can print it here even nicer. So we have test 1, 2, 3 string exclamation mark, new line test exclamation mark. And as I mentioned with printf, we can print directly to screen, but we can also use printf to just print another string like this. Then it will print it to the console here. You can use a bit more complex expressions than just provided here. I will add some more in the comments when I upload it to Moodle as well. For example, one of the simpler things we could do is if you want to add a floating point number, let's say test %f, and usually you would probably don't want to have like all the commas and so on. So you would write, for example, %.2f, which would mean that it will take the number and truncate it only to 2 commas. So in this case, as you see here, it took the whole number, but the commas, it stopped at printing 2 decimal places. It did not print the rest of the number, even though it could. If we would just have %f, it would do it. And there are similar, as you see here, and there are similar formatting specifiers, for example, for hexadecimal representation of numbers, so you can print things as hex. So for example here, let's add %f 0x usually starts with a hex number, and then the actual hex number let's say we want it to be always be from the left side field with leading zeros. We want it to be 8 characters or more, and then capital X makes capital X makes capital letters A, B, C, D, E, F, and small x would make small letters, and this 0x here is just added to be printed there as a piece of the string. It's not part of the thing, so we can actually leave it away. And as you see, it printed here the hex number properly. And even if we here remove the zeros, it doesn't change the literal. It just looks differently. It still has the zeros, and if we would just use %x, it would not print the leading zeros, and the number after the 0 then specify, you see here, how many leading numbers you have. So if we would have a 64-bit number, then we would, for example, have 016. And of course, to make it look nice, we can add the proper prefix indicating that this is a hexadecimal number. Now we can also print 64-bit number. So let's define one. 64 my long is equals 1 to 0x. Okay. So how does this get? S printf. Actually, we can just printf to console. Why not? S printf long unsigned. And now if we print it, it will print it. It is something that needs to be. I forgot to back the new line on the other one, so let's add here a new line. \n. It is important to use the right type in this format description, because otherwise it will usually always assume that it's only a 32-bit integer number. So like if you just use %u for a unsigned integer, it will only assume that it is 32-bit, and then this will not work correctly. So you need this long prefix to make the thing know that it will be printing a 64-bit number. Okay. So at this point we already have seen how you can print things to the console, which is quite useful. So if you are making some own programs for testing or something, that you can just print text to the console, this is quite nice. But you might also wonder how you can read some text from the console. So you might want to ask the user enter a random number and or something. So this is there are also helper functions for this provided in our standard library. For example, let's say we want to read 2 integer numbers, int my num1 and my num2. Int count is equals scanf. It stands for scan formatted, and then we use the same formatting as with printf, but instead of the values we provide, of course, addresses of these values so that it can alter them. Reference on this, reference on that. Yeah, and if we run it now, doesn't matter. Yeah, it says this scanf is unsafe, which I guess it is, but we can disable those warnings but by specifying a precursor macro. Okay, and now it's basically waiting for us to enter this text. So actually the reasonable thing to do would be first to print f. Yeah. So that we know what we have to do, and the semicolon at the end, of course. Okay, 1, 2, 3, 4, 5, 6, enter. Now we are here and it has read 1, 2, it's hex. Let's disable hex. Um, 1, 2, 3 in the first one and 4, 5, 6 in another one, as expected here by the format string. Also, it returned the amount of parameters it could read, so how many were filled. In this case, 2. So this is how we can read something in, and of course there are more things that one can do, but for now let's focus more on the on which other types of characters we can have. So currently we only use this char character, which is a single byte, and it usually can only represent values, well, it can always only represent values from 0 to 255, and it usually is used for strings which contain characters from the Latin 1 alphabet, which is basically the American ASCII extended with an additional about 100 additional characters, which are mostly used in European countries like U, some other letters, although not all, since they only had like 100 something available characters in the higher half of the character. If you want to use a completely different languages like Chinese, Arabic, etc., etc., then you need some sort of character which can hold much more values than just a single byte. And here, depending on the operating system, you will either see a 2-byte white character or a 4-byte white character. Generally, Unicode, these are called so-called Unicode characters, and generally a Unicode character can be up to 4 bytes in size. And Linux, for example, uses an actual white character which is 32-bit. Windows, however, uses a so-called UTF-16 representation, which uses 2-byte, so short type Unicode characters, and they are usually large enough to represent most of the typical characters from the Unicode code set, but for special characters, especially for the more complex languages, they are then made out of like that one Unicode character actually is represented by 2 of these white characters. Since we are here on Windows, we will obviously use those, so they are defined as vchar_t. And the thing is that this wchar_t is really something different on Windows than on Linux, so you need to keep this in mind if you would want to communicate binary data between those two platforms, that you either need to convert it to some commonly understood representation, or yeah, pretty much it's the only option. You need to convert it to some representation that both can understand, like UTF-8 or UTF-16, etc. So such a vchar, other than being a vchar, behaves like a normal char. You can initialize it as you like. Test. And what we can do when defining strings, we can use these escape sequences, which I think I showed you some of them already when we just talked about normal chars. And there is like a special escape sequence which allows you to specify a binary value for a character. So \u. This is especially for Unicode. 1, 2, 3, 1 F 600 doesn't matter, 1, 2, 3. Okay, and now if we see, does it show us? Yeah, and if we now run it and see what's in our string, yeah, it still wants us to enter something. So let's comment this out for now, since we don't want to break there. So, and as you see, this special Unicode value creates a character which looks like a smiley face. And of course, with a different, so basically it's a \u, and then you have a hex number which identifies the character within the Unicode and then character space. And you can have another number that will be some Japanese word, another number that will be some Chinese word, another number that will be a sad face, and so on and so on. So generally that's how this works. And of course, when printing to the screen, there are conversion functions that will take the strings and properly generate you the right characters automatically, like printf, etc. So if you even have a situation where you have like two characters, like a double character Unicode encoded which are on Windows, it will properly print it as one thing. The main limitation here is that what you generally want from your string is you want the ability to address things by index, right? Because if you want to get a substring, then you say, let's say I want something that starts at offset 5 and is 3 characters long, and so on. And with normal chars, you can of course do this. With Unicode, this works also nicely. As soon as you would reach such a special value which actually needs 2 Unicode characters to be encoded, you cannot just take one of them, because this will then yield an invalid character. You will then always need both. And when you are just addressing the array, the addressing does not handle, like, it doesn't skip 1/3, because it doesn't know what characters lie in the before this position in the string, so it doesn't know the proper offset. So generally, when passing strings, you would not use special characters from the Unicode character space as delimiters in any way. You would just use the normal ASCII characters that are common to all the textual representations, and then you kind of maneuver around the problem that you might have something that will take more than one character, and then you can still nicely decode everything. So you will not, in this Unicode characters, you will not find like a second half of a Unicode character which would be a valid ASCII character, basically. So it is not made such that like the first character is a starter and the next one can be any value, but the values that every subsequent character in such UTF-16 or UTF-8 encoding can have are set such that they will not collide with the typical delimiter characters that you might want to use when passing strings. So for example, if you have a path to a file, then you would want maybe to separate by backslashes, etc. And you can do all those things safely with a UTF-8 or UTF-16 encoded character. Just as said, the UTF-16 representation as used by Windows here does not, like, it's kind of simpler in the handling, because mostly this 2-byte character will be large enough for most characters. So you will very rarely find yourself in a situation where you actually would even use 2 characters to represent one. How to convert between them, this is a different story. So as mentioned, there are different encodings like UTF-16, which is used by Windows. And another encoding is called UTF-8. And this uses characters, while UTF-8 uses 8-bit chars. So basically with UTF-8, anything that is not standard ASCII will automatically be converted into some multi-character representation, while with the Windows approach only very few will be converted, and ultimately you want to have the Unicode itself, which is 32-bit characters. and this is, for example, what Linuxsoft usually uses as standard. Of course, it's kind of wasteful to do it this way, since most things that you would have internally in your program, like some paths, registry paths, sizes, numbers, file sizes, etc., even if it's in textual representation, it would only use the ASCII character set. So the Unicode characters are really only needed if you have like messages that you show to the users, if you are processing some text files, etc., etc. So the approach of Windows to by default use the UTF-16 encoding is kind of a very reasonable trade-off, because it gives you already a very large character space from the get-go, but only increases the size of the string by a factor of 2. Okay, so far any questions? No questions? Okay, then let's proceed. So as I said, except for the NTDLL and the Windows CON internally, all the Windows APIs are using those strings. Now it might be interesting to take a look on what string representation the NTDLL uses. And what it uses is a structure, something like this. Let's call it typedef struct string *p string, and first it has a then short length. So how long the string actually is. The string that as a string as what you as human understand a string you want to see, like if it's test then it's for, etc. Then you have maximum length, which is the amount of memory which has been allocated for this string. So the nice thing is that you can, let's say, allocate the 1 kilobyte string, and then every function that gets this object knows, first of all, how long the actual used portion of the string already is, and if it wants to add something to the string or replace the string completely with something else, it knows where's the limit, and if it would reach the limit, it will somehow return an error telling you that the string was not long enough. It's not quite as convenient as the STL strings, which we'll take on a look once we start the C++ section, but at least it is quite safe. And of course it has one more member, depending whether it's a ASCII string or a Unicode string, but most of the API use Unicode strings, so let's go with that. Small team buffer asterisk. The way you can allocate memory here for this string is twofold. You could either do the simple thing, so let's say this needs to be capital. So officially those are not called like string and p string, but Unicode underscore string and p Unicode underscore string. P is for pointer, and if you have the char version is ASCII string, so ASCII underscore string and ASCII and p ASCII underscore string for the pointer itself. And it's usually common with the Windows API that you define things like that here. So normally the simplest thing to define a struct, as you remember, is struct name. Struct name. What you can do is you can use the typedef, which we also said before that you then specify, let's say, name, and we call it, let's say, my name. And you can make another typedef to define a name asterisk p name, etc. And all this can be collapsed more or less into one thing. If you start by typedef, then you put the struct, then you put the name for the thing, then you make comma asterisk to get the pointer version, and then the name for the pointer. So this is quite convenient, and in the Windows API you will find a lot of structures defined exactly this way, including some dummy name before for the structure before it is typedef, which has mostly legacy reasons why you do it like this. Okay, so as said, we have, let's say we have our p string, is equals malloc size of p string. We are missing malloc as the lib has malloc. Okay. So here we have first our string, and now that we have our string, let's set maximum length to, let's say, oh, and the maximum length in this, in case of Unicode, is in bytes, which is kind of annoying. In characters it would be nicer. So for our use case, we could, for example, say, now let's, I mean, the strings that I usually create are then defined in characters, but for here, since one is compatible, let's stay within bytes. So let's say bytes. So let's use that off. WHRT times however many characters we want. Let's say 1024, and then we would define well, allocate our buffer is equals small t malloc maximum length. Like having length in actual bytes and not in characters is really annoying, because you always need to divide by whatever your character size is if you want to get to the actual count of characters. But in the Windows API it is done this way. Wait, WHR Stern, forgot the asterisk. And okay, so this is how you would define such a string in a simple way. There are, of course, a few downsides to this. First of all, you use 2 memory allocations, and then of course you need to, when you are freeing it, you need to remember that you need to free first the buffer, and then you need to free the actual string itself. So this is kind of inefficient. The advantage, of course, is that you can replace the buffer. So you could pass a reference to your string, and then something could set you a buffer on it, which would be kind of nice. But if you know that you are passing a string to something which just consumes it without modifying it, there is a simpler way to define the string. Let's put it in a scope so that we can reuse the same name. So we start with string, and then we just here add the size that we want. So we just allocate more memory than we need, and then we'll have the string. Then we of course need to still set maximum length. So usually you would have a helper variable. Let's go with the same type. Oops. Len is equals, oh no, let's call it size. No, let's call it length. Let's stick with length. Then we said just max length is equals length. Also, one thing I forgot, we should of course set length to 0 in both cases, because otherwise it will be just this debugger values or random garbage, depending on whether it's the debug or a non-debug build. Then of course we need to set buffer, but this time we don't allocate memory, but we just take our own pointer. First we cast this to something that has a byte size, so we can, although we could also use uint. Is this not defined? It's not defined here. Yeah, let's just go with char asterisk. So once we cast that, we can then add to this size of string, and then we need to cast the whole thing back to varchar and a small t. So this way we only need to free one memory block, and the whole thing also needed only one memory allocation, which, as I mentioned during the last lecture, memory allocations are quite expensive computational wise, simply because the memory managers, since they want to be able to handle any size of memory requests, etc., are usually quite non-trivial, because they are very generic. So being able to save on memory allocations and only allocate once is a great improvement. Of course, given this size of memory, you could also get the memory from the stack, but for strings you might want to maybe have a 64 kilobyte large string, as would be the limit here for the short type. So usually allocating those strings from the heap is the way to go. Yeah, okay, so any questions so far? Okay, if there are no questions, then we'll proceed. So with strings, that's already for now everything, since it's not that complicated. As I said, I will comment this with a very long list of different helper functions which you could use. But generally speaking, it's just working with arrays and keeping in mind their limitations. So now let's start a new project in which we will take a look on actually putting the knowledge which we have aggregated throughout the past lectures to some good use. We'll create a simple list object, so something that we can add elements to and remove elements from without yet using a C++. So the way we do it is we define some element for our list. So let's call it stocked my list element, and it's my list comma asterisk my list element. Oops, typo. Okay, and this list element in the simplest representation would only have a pointer on itself, or rather on the next element in the list, p next, and that would already be the whole thing. Of course, we want some payload data, which we will add to it later. We will see how we do that. And then either you could just have your list basically defined as just pm list, let's call it my list, let's call it global my list, and of course an asterisk, that's a pointer, null. But this is kind of the boring way of doing things, so what we will do instead is we'll create an own element as such to hold a few data, because like for our list usually we would want not to we would want to have not just like the first element, but we would, for example, also want to have the count of elements in the list, or we would want maybe some even additional properties. So it's nice to have an object that could hold that. My list. Can we define everything here? Oh, I think we have a typo in element, because it's the L is here capitalized, which we don't want. Although it doesn't matter, we could just go with that mistake. The compiler doesn't care. And this thing will now get a pointer to the head and a size u count that will hold the count. And now we can define our list actually as a variable. Let's say list, and the thing ideally should be initialized, let's say with null and 0. Okay, and the way this list is supposed to work is that we simply create an element of this type, or something that's bigger than this type, and we just assign that the list head points to the first element, and the next element which we add to the list will point on the next, and so on and so on and so on. So it's basically like a linked chain that starts where we know that it starts, and then it just goes. And it has many limitations. Practically, for example, you cannot address an element in the middle. You always need to start at at the end. And unless you count and remember how many elements there are, the only way of finding the count of elements would be like with a C string, by just starting at the start and just going to the next, until you find the element where the next element is pointing to an invalid value, usually the null value. Okay, so let's say we want to store some data. So let's create a data type. My data. And this thing just needs to contain the list element as a first entry. And as you might remember from our structures lecture, in any case, when we get the starting address of this thing, the starting element will be identical in both cases, since it's just a memory block where the different members are added together. And we add some data, say for integers. Okay. This is the C version of doing things. The C++ version of doing things would be to use inheritance, but this is not something normal C can, and that is something we might do later, but not for now. So let's again define our list. My list. Let's memset it. I have a typo. Yeah, I have a typo. The Y is missing. My list. Okay. My list. Okay, so we have here my list. We take the reference on it. We want to zero everything and size of list. That's another way to initialize it. And now, of course, we want to somehow put an element into it, or let's say we want to add 10 elements. Let's make a loop. That will add 10 elements to the list. Then we'll need to create those elements. So we have this data type, and P should be capital. P my data is already pointer. P data is equals data malloc size of P data. Then we can set those P data, or we just set everything to 0. Let's go with this approach. So if this is already a pointer, then we need to use here. What we could do, because like this gives us the right size, this gives us the wrong size because this is just a pointer, but we can actually kind of dereference the pointer, and then it will give us the right size again. So we can do it either way. And let's say that we want the first value to be the loop count. And then we need to add it somehow. And for this, of course, it is very expedient to create some sort of helper function. Let's say void add to list, or let's call it append to list, which takes then our list as a pointer and the new element. But this thing will of course work with this my list element, p element, and of course we could create like append or insert. So append, usually the way it means is it appends at the end, while insert inserts at the top of the list. So let's create both. And let's first go with insert, because insert is simpler. So it takes an address on our list and it takes the element to be inserted. Yeah, it is of course complaining here now that it's kind of not the right type that the thing would expect, which kind of makes sense. So how do we work around this? Well, there are in principle two ways how we can easily solve this. First of all, we can just rename the file to a C file, not a CPP file. And this will change the rules how the file is compiled. And at this point, it consumes it just fine. The thing is, just normal C does not perform type checking on pointers, which is pretty annoying. But given that this is how we are supposed to kind of, in quotation marks, derive objects in just C, that kind of makes sense. But it's ugly. The other ways, so if we switch this back to CPP, would be, we could just give it a reference on entry. This is still still resolves the exact same value. So if we want to resolve those, let's call it in 64 test1 is equals, well, in 64 p data and test2 is this thing. They all resolve the same value. If we put a breakpoint and run it, we will see that we have some number, and if we just check the other variable, we have the exact same sum number. So, well, that's the other way around. And of course, the third way would be to just hard cast it from one type to the other. So this is type of p element, so we would just keep p data and just cast it like this. That is kind of the most ugly approach, to be honest. So let's just stay with this approach, because this is somewhat nice, and it's compatible with C and C++, and it doesn't like usually having castings. You want to avoid it if you can, because when you're later reading the code, then it's always a place where you have to think, okay, what is it doing? Is it safe to do that, etc. Because as we have learned in the past, you can cast things in any way, even if it makes no sense or will result in unpredictable behavior. So usually once you start using and learning to read more C++ code, you would always be careful when you see a cast somewhere and think twice about what it's doing there right now. So to save on your brain power, you would want to write your code such to avoid unnecessary casting, so that when you're rereading it years later, you don't spend brain cycles on thinking whether a certain cast is safe or not. And this approach kind of guarantees you to some extent that it is probably safe. Of course, this element could be somewhere else, but then everything would be broken anyways, so this thing just must be the first one, period. Right, and now we of course need to implement our insert function. So this is quite simple. So we have our list, which has this head, right, and we have this element. So first of all, the element itself has this pNext, which we will set to list head. Be that be that null or not, doesn't matter. Wait, we forgot. Yes, with this asterisk is once too much. So if we have this p, then it already includes our asterisk, so we don't need to add the p to it. Okay. And then the simple thing we do is then we set head to be our new element. So basically, when a new element comes to the list, it is placed as the first element in the list, and then whatever was before the first element now is being pointed to by the element's next variable. It is very simple, it is very fast. So as you see here, it is quite nice. Appending to the end of the list is difficult, as we have said. If our list only contains this head variable, then we only know one end. We could of course improve the list by adding a tails variable, which would contain a pointer to the last element in the list. This way we could efficiently insert things from both ends, but this will be homework, so we won't do that. That will be a task for you during your Easter break. So what we do instead is we just need to find the end. This is by far not as efficient, but of course something that that can be done. So we have our list element. Actually, let's go just with the element without the p, and we make a double pointer. So a pointer on a pointer. P tail is equals reference p list head. So we have a pointer which points to the pointer which points to the first element in the list. And now we need to find the end. So let's make a loop. We don't need any initialization. Asterisk p tail is not equals null. So the loop will run until the pointer which tail points to will be a null pointer, but not tail itself. Tail itself will be something else. And then of course if it isn't yet, so we need to go further, then we just write p tail is equals reference asterisk p tail capital T next. So we started with pointing to the head, and then later we'll be pointing to the next entries in our list. And the for loop doesn't actually need a body. Everything that is interesting for us is already done here. In principle, we could also use a while loop like this, and then just write while and remove the two semicolons, but I kind of like this way of doing it more. And then once we have found the tail, we can just simply assign to it the new element. So obviously, oh, and we forgot actually something important. We want to keep track of how many elements there are in our list, so we also need to increment our counter here. Okay, so yeah, so the way it works is, as you see, quite inefficient. If we would have like 100 elements, we need to make 100 operations. Actually more, but like with operation you mean like a set of sub operations. So in this case, compare and then go to next. We call it one operation. And if we have 1,000 elements and 1,000 and so on and so on. So for a very short list, like 10 elements, doesn't matter, just a few opcodes, that's fine. But as soon as the lists get bigger, then those sort of linked lists become inefficient. So it is important here to manage that reasonably. An improvement, as mentioned, is to make it a doubly linked list, i.e. add here a tails, p tail, and add here a prev, and then make the list the list elements point to each other in both directions, which is quite nice, but of course it still keeps the issue that you cannot address randomly somewhere within. You need to start at one of the ends and then go however long the thing is until you reach where you want to go. So to demonstrate this, we could first of all we would like to print our list. So we need a way to do it, and we can just do it manually, of course. That's the simplest approach. Let's do that first, and then we'll see how we can make this more elegant. So we just start with p my list entry, my list element. That is far too long of a name. Let's shorten that, my entry. I'm too lazy to type that each time. Okay. Now we have my list and my entry. That's much more reasonable. P entry is equals list punct head. Okay. Now now we want to go through it. So actually we could make a for out of it. For. So we start with entry. Then of course we check whether entry is not 0. Entry is not null, and then once we are done, we can advance entry to be entry next, and inside of our thingy, let's see printf data1 doppelpunkt %. Let's use %i for integer, like %i, %d both give you an integer, %u gives you an unsigned integer, and so on. 2, 3, 4, and we make a line break. Backslash r backslash n at the end, comma, entry. It was the wrong entry. Let's go with my data. But here, of course, then we need the cast. So just cast the list head to my data. P my data, of course. Right. And this thing here now, of course, have the other thing hidden in entry. And we need a cast here. So it kind of is much more convenient to switch to actual just C, because then we can wait, entry next, P data. That should be fine. What's complaining about? Other one of those is not correct. This is a dot. Not the other one is a dot. This one is a dot. Right here. So we want entry data. Yeah, data 1. data 2, data 3, data 4, data 1, 2, 3, and 4, and semicolon. Okay, so when you run this, it will nicely print here our list. Since we used the insert option, it's in the reverse order. We can now, since we already added that function, also append. I mean, if we run this, we will now get the right order if our function works correctly, and as we see, it does. So this is of course one simple way to go through the whole thing. And we can in various ways make this more elegant, but for now this is good enough. So one thing which we might, for example, want is to be able to remove an element from the list, right? So let's say void at list remove from list, and the thing will of course need to take the list itself, well, a pointer on it, and it will need to take the element which is to be removed, obviously. So and then we will need something to find something in the list, which we will do as well next. Okay, so removing is with a singly linked list, not quite as easy, since we need to find first where the thing goes. With a doubly linked list, remove would be much more elegant, because since it knows both things that are on both sides of it, it can cut itself out from the middle in a reasonably nice way. So, but we don't have a doubly linked list yet, so we have to do it the simple way. Right, so my list, oops, let's go with PHP. No, it was my entry. My entry. Let's pay all the next. Let's call it. Reference list head, and we can copy our this thing to some extent. Just call it differently for now. Or we could just call it pold, that's also good enough. Let's just call it pold. So this thing goes through the whole thing. As you see here, I have defined it slightly differently. So here we use the non-pointer version, then we need 2 asterisks, and if we have a pointer, then we will need 1 more asterisk to turn it into a pointer to a pointer. And of course, inside our loop now we need something to do. So we check if since this is a pointer to a pointer, we want to just the first pointer value, so we dereference it. And if this is equals our element which we want to remove, then well, we found it. Actually, we could change the function and make it return a true or false depending. Don't we have a boolean? Defend. No, we don't. Let's include Windows H. So as I mentioned earlier, there is no boolean in that sense in just C, only in C++. So there are just booleans defined manually, like bool, and this is defined, for example, by Windows, and it just uses an integer. Right. So we return false, and this false is also just a preprocessor definition for 0. The real boolean false would be lower letters, but that would not properly compile in a C, not C++ application. Same for true. Okay, now of course the remove procedure itself, which is quite trivial. We just take the old thingy and we make it point to the next thing our old would be pointing to, be that null or something. So it's not that complicated, but of course it is extremely inefficient if it is a singly linked list. So let's do do. Mm. Um, Version from and then from one and yeah, and here of course to do. That's the same to do for those both, and later we will summarize all the to-dos in one place so that nothing can be missed. So this remove from list function can be made, as mentioned, much more efficient once we have this doubly linked, because then we kind of automatically can resolve what the old thing would be. The downside of this doubly linked is of course then you need to link both things around, and you also will need some special cases for when the elements at the very beginning or at the very end, in which case then the next entry would be null, and then depending on which one of those two is null, whether you need to refer to the list head or the list tail variable instead. Okay, and then of course we said we need a way to find something in our list, so let's create a find function. P my entry find in list, and of course provide the list, and then of course we need to somehow be able to universally find things, so we can define as a function pointer type def bool asterisk t my find func that will take an element p my entry per entry. It can take, it doesn't have to, but it's nice to have a void asterisk param, which can be anything. Should be capital. Okay, and that's already it. So now this function will take two things: our function and a void. The void param is strictly optional, so we don't need to use it if we don't want to. So end of group plist head, right. And now what we do is simply we check if our function once invoked with the current element, and it gets the parameters just in case they're needed. If this thing says true, then we found what we were looking for. So it that's not data, that's entry. Per entry, this is no longer needed. Or the other way around. That's the pointer, okay. Right, and here, so if this is true, then we can just return p entry, because we found it. And in the else case, or rather when we don't find anything, we just return null. Okay. So let's then define a function for our special data case. So say all I find data func. It needs to have the same prototype as the other one, and it has to do something. So first of all, it will cast from p entry to our own data type, because this is what we are interested in. And let's say if data1 is equals let's say param is a pointer to an integer. It could also be a whole structure containing complex information. We would also have like one liner just return like this. Okay, and now let's use the function here. So my entry found is equals my finding list according to my finding list reference on list. Then we need our find function, and then we will need the parameter. So we said int param is equals, let's say we want to remove the fifth one, reference param. Okay, and if we have found it, we need to check whether we found it. Then we will remove from list reference list, comma, and the found thing. And then if we run everything, and if it works as it should, the number 5 should be missing from our printout. And as you see, it is. So that worked correctly. And we have successfully removed one entry from our list. Is this clear so far? Any questions? Okay, no questions. That's good. Okay, so let's continue. So what else we would want to have? We could have a function that finds in reverse, so like it searches from the back, but that's quite trivial, so let's not do that. Okay, I think with regard to this class we already have like most of the functionality which we can have with only using C and not C++. So let's properly formulate the homework for the next lecture. Oh, it's day 10/04/2025. Update the simple list or the single list. Okay. Okay. And those two functions. So this one will be simplified, as mentioned. It will not need to iterate through everything. But in turn, both of them will be, in that sense, a bit more complicated, as the as you always need also to update the previous pointer accordingly. And the remove function can get rid of the loop searching for it, but it will add it will be added to special cases for the situations where we have something that is either at the very beginning or on the very end of the loop, of the list, because then you have to update not a pointer inside an element, but then you need to update the pointer inside the list structure itself. Oh, and we forgot one thing, of course. Count on success must decrement our loop counter, otherwise we will get the wrong value. in our list. Okay, so this structure is complete, and we can proceed with something that is a little bit more complicated. So such lists are, as said, quite convenient, but if you would want to find something in the list, you have to search through the whole list, as we seen here. So the worst case when you are looking through the list is that the very last element you look at will be the one you were looking for. So this is not really efficient. So what we would want is something that would allow us in a much more efficient way to find things. So let's start again a new project. We'll call it a hash table. Okay, great. Okay, and let's because we are lazy, copy at least some things from here. Genau. So we have my entry. The my entry thing can will be in fact will have a pointer to a next entry. So it will. So such a hash table contains a list, but it also needs a few additional things like a hash value. Let's say a unsigned int hash. Okay, and it will also then, depending on what will be the key, it might need some something to store the key. But for now, we will only just give this the hash value and the next, and nothing else. And about the rest, we'll think later. We'll call this, of course, my table instead of my list. The thing will now be slightly differently here, so it will have as a count, obviously, but also a bucket count. And what previously was kind of called the head will be now called buckets. In principle, of course, this could be, if desired, implemented like each entry inside the bucket could be doubly linked, but for now we go with a simple bucket, right? And bucket needs to be the last thing because we want this to be an array, which we can. So so basically, the buckets thing is a array of singly linked lists. We could later upgrade it for to doubly linked lists, and we want this to be the last entry, such that we can use the trick I showed you with the string to just allocate one thing for this table entry and not need to do two allocations. The alternative design could be, of course, that we say that this is a array of pointers that we can then malloc with malloc, which is less efficient, but it is much more convenient, since then we don't need to change the table element itself. So we'll go with this design. So we have then we can of course move this back at the beginning. So we have our arbitrarily long array of buckets. Then we have our bucket count, which will tell us how many entries this array has. And then of course we have the count to count the elements. So then we will also need some data type that will fill into this. So let's copy this thingy here. We will call this still my data, and it will still have a my entry. But what it will also need, in addition to these entries, it will need some sort of key, which will indicate which will be the key by which we are entering things into our table. The idea of this table here is that depending on the type that you have, you can create arbitrary things as keys. But then, of course, the data object itself needs to hold the key as part of itself. An alternative approach to this would be to just have some arbitrarily sized key object here. So that would be just a array byte asterisk, but this would then require again one more allocation. So we will try to go with the most space efficient approach, where our entries for the table already keep the data and the key all in one place. So let's go with int key. We will be lazy, but we could later change this to a string. Or actually, maybe that would be more fun. Let's go with the string being a key. So let's say with char key. Oops. Key, and let's say we limit the key size to I don't know, 25 bytes. Sounds like long enough for a key. And then we have our data here. We could of course have any other order of entries, except of course that entry needs to be first, but for the other members it would be whatever we want. Okay. So again we copy from here our some of our code that we already have. Of course we need to change everything to the table. So my table, this is table, size of table, everything set to 0 at the beginning. Per my data, okay, my data e, and of course my data key s printf s, comma, key, comma, 25, comma, test, double point, e, comma, e. So the key will be just the test double point, and then the number as a key. Then the data will be the data, and then we will of course need another function, tree add, tree insert, insert to tree, which will take of course a reference on our not tree, insert to table, table, and comma, of course then the data we are inserting. So we need to write this function. Okay, write function insert to table. It takes of course p table and the element, but the element here again, it's just complaining that we are not yet ready with the whole thing. Will be of type my entry, pay my entry of course. That will complain at the bottom still here that we need to do this. We need the reference on this. Okay. Yeah, this is again a CPP file, so yeah, let's leave it as this. We could switch to a C file, but it's fine if it's more restrictive. Okay, so the way this, the idea generally with such a hash table is that first of all we have the key, and we generate from the key somehow a hash value, so something that is a 32-bit number. And then we want to we take from this hash value only a portion of it, which is which is long enough to be able to cover all the possible indices in our array of buckets. And of course, if we have not enough buckets, then we'll need to generate new ones. And ideally, we would want to have one entry per bucket, because this gives us the best performance, but this cannot always be guaranteed. So when we are adding elements, we'll always check how many elements there are in the table, and if we see that we have more elements than buckets, then we will grow the table such that we have enough buckets to accommodate all the elements. In reality, some of the buckets will be empty, some will contain a couple elements, but this should not be more than a few, so it will be reasonably efficient to, once we have identified the right bucket from where to retrieve an element by key, then there we just check those elements for which element first just the hash value matches, which is a very quick comparison. And of course, since the hash value has only 32-bit, while so 4 characters in size, while the key is 25 characters, there will be many 25 character long strings which all, when hashed down to the hash value, will have the same value. So obviously once we found an entry with the same hash value, we cannot rely on this. We then actually need to compare the keys, but which, given that this is a string, might be and it might be a longer string, so it could be much longer than 5 characters, so it will be computationally intensive. But ideally, in almost all cases, it is just a sanity check to check that, okay, this is the right entry. It is very unlikely that we will have multiple entries with the same hash values, unless of course our hash value is really bad, which can happen, and we will try to avoid that. Now of course the whole thing will be a bit more complicated. We'll need to add a few more helper functions to it, but I would say just let's start with calculating the hash value. So int hash is equals, and first of all we'll need a function for this. So int hash func, which takes the thing here. So hash func von p-entry, and we need our hash func that will work with our special sort of, so let's call it my hash func p-entry, and the thing will now be, this will be a specialization which works on this type of data. So whenever we create a new data type, we need to provide a appropriate hash function for that. So here our hash func for the string, let's say int hash is equals 1 2 3 4, and now let's see for char if this ptr is equals key ptr asterisk ptr, so it's not null, and ptr plus plus to go to the next. Right, so hash is, let's say, or equals hash shifted by 8, and hash or let's maybe take XOR. No, let's take XOR everywhere. Yeah, that is better. XOR here and oops, and XOR there with our ptr. It's not a good hash function, but it is a hash function. It will generate some output which depends on the input, and it should use the whole key space. We will later maybe look into generating better hash functions, but for the start this is good enough. So now we have our hash value. So the next thing we need to check is of course if we need to make the bucket list bigger. So if table bucket count is less than table count plus 1, then we need to reallocate the resize the buckets. So void resize bucket list, or resize buckets. Let's call it just resize buckets, and we should go with size t, new size. Okay. And for simplicity, we will try to always resize by a factor of 2. So of course, if we have a value, then value we shift it by 1, that multiplies everything by 2, or else we just start with well, 1 is boring. Let's start with 1. Why not with 1 entry? Right. So if this yeah, and of course table is the first argument. Okay, so we pass the table. Then of course if bucket size isn't 0, then we just create one entry. Let's create 2. Or actually we could also start with some reasonable amount. Let's say we start with 8 entries. And then if we have exhausted those 8 entries, we will then multiply it by 2. So we can maybe write it in comment. Shift. And then we'll always multiply it by 2. This will make our computation for the indices much more computationally efficient. Okay, this function will need to be obviously implemented, but before we do that, let's assume we already have some entries in our bucket table. We actually could initialize the thing with an empty pre-initialized something that contains already some values, but for now let's just assume it. So if we have this, then the next function we'll need is size t get bucket index. This thing, of course, like everything, takes table, and then it takes the hash. We will implement this in a second, but here we now write int index equals get bucket index from table and hash. In principle, logically, we could actually have this moved down. Okay. And if we have the index and we already know that the bucket list is large enough, then we can go to bucket, to table, buckets at index, and there we could enter our element. But for this, we'll again make a helper function. Let's set it here. Void add entry to bucket, which takes the table. Actually, we could just move everything up. That would be more elegant. So, oops, not here. There. That is more elegant indeed. But then it needs also the hash value. Okay, so we will do it like this. Okay, so we start with this having here. We have this entry thingy, which already has a place for the hash value to go. So we'll just pre-populate this. This way we don't need to carry this function along. Then we have our resize, and we make here our add to bucket, which takes our table. Oops, and the entry which is to be added. Okay. And this is done. Then let's see here. So here we have the index. So the index we now get from the entry itself, from the hash. Okay, so we have and of course index. Since we have perfect forward definitions, we need to have defined before. So we have the index, we have the bucket, and now basically the function is as our simplest insert function was. So it's quite trivial. So we have our entry. Next is equals bucket index, and bucket index is then equals this. And we will here's a smaller typo. And but since we will reuse this function somewhere else here, we will not make this function increment the counter. This will be left to this the insert function. Okay, so our insert function here would be complete. We now have two more things to go. So this bucket index, this is because we have the power of 2, that can be made quite efficiently. So basically what we would want in a simple way is size t index is equals hash table bucket count modulo hash modulo bucket count. So basically this modulo operation is a it gives you the rest of the division. So and computationally it's as expensive as a division, and as we talked earlier already, divisions, especially on very simple processors or microcontrollers, are very expensive. So usually you would want to avoid using a division or a modulo, which, as said, will take just as much computational power. So what you would ideally want is something that is more efficient, and you can do this in fact using much simpler operations, but only under the constraint that bucket count is a power of 2. So basically each time you grow it, you have to double it. You just multiply it by 2 each time. So the way we can do it is, and of course we would return index once we have it. So the way we would do it is we have our index, then we have our hash, and then what we want is basically you just want to map out all the higher bits which might be set, but which would make our index go past the allowed range. And so we can use the AND operator, and then we use the bucket count, bucket count -1. So let's see if we can demonstrate this quite easily. So we are, let's say, decimal. So let's say we have a bucket count of 16. So you see here we have 1 and, well, zeros. If we go minus 1, then we get here pretty much all the lower order bits set and none of the higher order bits set. So we get a mask which will clear everything that's higher than 16. Well, actually higher than 15. And this works as long as this bucket count is a power of 2. Okay, good. So we have our index, we have our add to bucket. So now we need our resize function. So the resize buckets will need to be able to handle 2 cases. One case is of course when we have no elements in the list and it just creates them. That's super simple. But it also needs to be able to handle the case when there are already entries there. So we need to save the entries somehow and then re-add them. So this is actually quite easy to do. We create a pointer to the first entry. We call it p head. Okay, now we make a loop for size ti is equals table bucket count I minus minus. We want to go from the other end so that we don't change the order of the things each time we add something. Even though we are not maintaining much order, we want at least to not change it every time. Okay, so we have here our per bucket entry, reference per entry is equals p is 1p too much. Then we don't need the okay, right, p entry is equals table buckets here is I, and now while p entry is not null, we could just write it like this, and we need a temporary variable p next is equals p entry next. Okay, now p entry p next is equals our head, then our head is equals p entry, and last p entry is gleich p next. Okay, so this will iterate through every entry in every bucket, collecting them all into a single linked list. And now what we can do is we can get rid of the old buckets, assuming there were any to begin with. So the way free is defined, if I recall correctly, you can call it on the thing if it's empty, but let's make this particularly safe. So if bucket count, then, or rather maybe not bucket count, but just if buckets, then to this, and the last step will be just free buckets. Yeah. Then we need to allocate new buckets. So buckets is equals malloc. We'll need to cast to wait, mp entry asterisk, yeah. And we have here a new size and bucket count. We should call it new count. New count. We have a new bucket count, and now we need to reinsert everything back to the right indices. We'll use the insert entry function for that. So while p head let's be lazy. Let's say this is here p head. Okay, add entry to bucket. Add entry to bucket. Table. This table entry is head, and then head is next, and then repeat everything until everything has been moved. Okay, and that should be it with regard to inserting things. Now finding things is a different story. That will need some more code, but we can here we are missing a function. We need the hash function. Okay, and what we might also want is some method to print it so that we can see what we have in our table. So let's add here a void iterate table. So the iterate table goes through the whole table and calls a passed function similar to the find thing. But the thing does not need to have a return value. Though we could give it a return value, we could make it capable of aborting the iteration. So let's go with that. Boolean asterisk p iterfunc. Let's go to iterfunc, and it takes a entry. Takes an entry, and it takes a void asterisk, and the whole thing takes a void asterisk param, and then let's as the next thing already define our iterate function. So boolean my print entry, which takes p entry and void asterisk param, capital P, that we'll implement later. And the usage of this will simply be iterate table, reference table, comma print, comma no, we don't need a parameter, but it's nice to always have it, because if we need it, we then don't need to change the code. And then of course our print function here. So we can copy, let's start with this. So this goes through all the buckets, and then we are of course going through the entries, but of course we don't want to modify them. So this we can actually implement in a simpler way. This will be a for loop. P entry head is equals table buckets at e head is not null, head is not null, or just as said, we can just save code, and head is equals head next. Actually, we didn't need to copy anything. It's just as simple as that. Then of course call our iterator function on our provisoric. Well, maybe don't call it head. We just call it pointer because it will only be the head for the first entry and then not more anymore. So let's go with just calling it pointer, and then we pass our parameter. And if this is not, then we want to return. And actually, we could even pass this value return. Maybe that's useful for something in the future, or maybe not. But it is not really a major complication. Okay, so this now the print function. So here again we will want something of type my data. Data is equals per entry. Now printf. Okay, so entry. That's what I key is equals %s, comma value that we copy from the other project. Value. Yeah, just key, and the rest then is just this data. Data, and of course the first one needs to be our key thingy. And new line, good enough. When we run it, it should print out the content of our table. We forgot to return true. Okay, something is not right. I is 2 per data malloc size. Critical error detected. What did we break? Let's step through everything step by step. Probably will be some sort of memory corruption. Right, so we allocate the thing, we mem set the thing to 0. Data, okay, yeah, this is all zeros. We print string to it, but only the very first part, the rest is intact. We set I to something and then we insert. So let's see, we hash our function. That should go 1, 2, like 5-ish or 6 steps. Yeah, okay, it was however many it was. We have our hash value, which is, well, looks random enough, at least for starters. Then we have here our bucket resize operation. So we see that there is nothing to do. New bucket count is 8, new bucket count will be 8, so this is fine. There's nothing to do. Now we do our insert operation. So we get bucket index number 6, which is a valid index given that we have 8 buckets. So bucket at index. So this thing is then null. It stays null basically, and the index buckets at index will become we did not initialize our buckets here. Memset. And there's another very glaring bug. We did not allocate enough memory. 0 and size is this. Suck. So one issue was that here we just added count, but obviously we need to multiply by the size of every entry so that we have enough actual entries. And the second issue was that here we did not initialize the memory, so we need to initialize the memory also with 0, so that we don't have, so that a bucket is either null if it's empty, or it is not null well, if it's not empty, because if it's some garbage value, then it will not work correctly. We can restart the thing and see if it runs. No, it's still broken. Let's see. Okay, so we still have a problem with the. This happens for the second. Okay, it actually worked a few more times, but then it still crashed at the 5th operation. Let's see, did we forget anything else? So we initialize all the buckets, then we insert. We can test, for example, if it always crashes at the same number, so if it's at least reproducible, so it crashes at 5, we repeat that. Okay, it always crashes, it crashes randomly, sometimes at 4. So this is a very unpleasant sort of bug to debug, because it is somewhat unpredictable. Now it crashes at 3. So let's see. The best approach here is to really just go through the code and try to find a bug, let's say manually. So this definitely should be right. At index, we take the index. This also looks correct. We can also note that it happens, we start with 8 entries, right? So it doesn't happen, so we only call this function once, and then it happens somewhere during just doing the insert calls. And also from the fact that the bug triggers when malloc is invoked, means that some of the memory used by the allocator itself got corrupted. So this gives us also a hint what might be going wrong. So somehow our insert function must not work as it should, because this is the one thing that we call multiple times, this add to bucket, which then somehow fails. So we put a breakpoint here and we will inspect this for the correctness. So we allocate something. Now let's put it here. We have the indices, so index 6 as set sounds valid. So this assignment here, bucket entry, you can inspect that we have some hash value, and the next is for now null. Since this is the first entry, this will also be null. Okay, right. Next entry, we want to set it at 7. 7 is also a valid value. 4 is also valid. 5 also valid. 2 also valid. And it still crashed. Do we allocate enough memory? So for p data, that is definitely enough memory that we allocate here. Right? That was the bug. P data is of course the pointer, while the m data is the actual data object. So here we have been allocating for our entries not enough memory. So let's try it again. Okay, that didn't crash. Didn't print anything either. Let's see. Let's put a breakpoint here. Okay, so we have our table. It claims it has 10 entries. So in principle, bucket count, bucket expansion should have even worked. But it somehow didn't print anything. So we need to find out why. So print table. We start with the buckets at the, well, here we actually don't care for the order, but bucket. If it's false, then false, else true. Let's see. So we enter here and buckets from, well, the last entry. Let's see. Actually, we can just inspect the bucket table quickly in the memory view. And it's entirely empty. That is not good. So we have somewhere another bug which makes us not properly populate our bucket list. So first of all, here we can change this to go the way it's expected to go with e less than suck e plus plus. But then now of course we need to find out what else might be going wrong. So we have our table. We create the list correctly. So add to bucket must somehow not be right, but this obviously here we have a small copying bug. We obviously need to assign next and not next entry when copying the name. The small mistake made its way to the code, and now we already have a proper printout. The count of elements also seems right. And one thing which becomes apparent here, of course, is that our hash table has a somewhat random order. Of course, the order will always be the same each time we run it, but it will not sort in any, for a human, intelligible way the entries. They will have just the internal order based on the hash values, and also it might work such that when the table grows, that the elements will end up in other buckets and the order here will also change. The only thing that our code preserves is the order within one bucket, but this is kind of not really useful in the most cases. In some cases this is nice to have, but in the most cases it's not necessary. So what we are still missing now is the ability to find some entry in our table efficiently, because that's like the most useful feature of our table as a data storage structure. So let's do this now. So we want something that will return us a pMyEntry. Find in table, or find by key. Let's call it find in table. The thing then gets the table, like the insert. Then it will need a hash function. Hash function here, and it will also need a compare function to do the final comparison. It will be a boolean cmp function, which takes it can take an entry, but then we need to take the key, but we don't know the type for the key, so let's go with void per key. Then we will need to pass a pointer to the key. In principle we could add a second param parameter, but I don't think that it would be useful here. And worst case we could just misappropriate the p key as a param, since it's a void pointer, so it can be anything. Okay, so the way we will be using this is quite simple. pdata, pfound, ptable, table, comma. Then we have our hash function. We have our mycmp, and we need a key. So the key would be char key is equals test 5. My compare function and the key. It can be a void pointer, so that's fine. And then we just need to implement the my compare function. In my compare, and what did we say it takes? It takes those two things. p entry. Actually, we could like actually make it simpler. P L key, left key and right key and R key. And then we have P. Let's say that this L key as lookup key and R key is the value that we have to compare with. So actually we can make it like this. And since we know it is a string, we can just return store sample char L key comma R key. Let's just copy this and change one letter. That's the most efficient way of doing that. R key, and this must be equals 0 because 0 means match. So the string compare function gives you 0 if the strings are equal, 1 or -1 depending on which of the two strings is bigger. But we only care here for an exact match, so we use this string compare function, and voila. What is it complaining here? Right, of course we need also then a cast, and we can check if we found it. Oops. Found. So if is equals null, then or rather it's not null, then we have found it, and then we'll do something with it. But for now, let's look for it. So searching something is not that difficult. We first, of course, need to calculate the hash. Int hash function from key. Right, but our hash function takes entry. That is annoying. So let's change the hash function. The hash function. Yeah, that is not the prettiest change. Because this will mean we need to pass the key here, table entry, and then comma. One after the other, one change after the other. So first we change this, then we have here the function. Where do we have? Whoops! Insert. Set the table. So this will void stern key, and here we will need to add void stern key. Okay. Then we go here, comma data key. It's not as pretty because it adds some minor complexity, but it's okay. And then we go back here to our hash function, which then will just take a key as a key. Right, okay, so we have our hash function now should work correctly. We have our hash. Now we get the index for this hash. Zack. Now we get the bucket. So and we'll want to go through the thing. So we will grab this from here. Buckets from index. And now we check if pointer hash is equals hash. That's already a strong indication that that's the right entry, but we need to be sure. Compare. And this is complicated in as far as now that would be now more convenient if that would actually take an entry as a as an entry, as a value. So let's change it accordingly. Okay, then this will need some more trickery. So we have defined the key here, but we kind of would want to have the key in our entry as well. So what we can do is we can have a some empty array. Let's say char asterisk char key from 0. So this is kind of a empty array. We can use this as a pointer to whatever is to be pointed next, and which type we use here is not necessarily relevant. Char is just convenient because it has byte-size resolution with regard to alignment. Could also go with void asterisk. Let's go with asterisk key. So this in principle should be good enough. It will give us an address. Okay, where were we? Here, right, so we have our compare function, which will take the current entry, and the key to compare it to. And if this is true, then we return pointer, else we return null. Now we can save some lines like this. Okay, unknown array size is not allowed, that should be allowed. But it doesn't like this, so okay, well, let's do it differently. Generally, the idea is that the definition will be that there are two ways how we can elegantly solve this. We can either say that the key is whatever is next after the entry. This is one approach. And the other approach would be to add yet another helper function which retrieves the key from our own data type. But for simplicity, let's go with the very hacky approach. So this is char asterisk plus size of p entry. And in principle, we would then need to cast this to our key type, but since our key type is char, this is already good enough. Okay, and if we found it, we print f. And yeah, lazy, we just take this here. Found key. Okay, let's see if it works. Right. I need to change all of that. Also, since we know the key, then we don't need to print it. Now let's print it, so just to validate that we found it correctly. Okay, so we have our found function. We go in, we calculate the hash and the index, so we know it should be in the bucket 11. So we have the first entry in the bucket 11, but it's not the same value. Wait, or is it? I defined it as unsigned. So let's quickly ensure that we always have all the hashes as unsigned value defined. It was the same value, just was represented differently. Right, okay. So we repeat from the get-go. Zack, 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 zack. Now hash is the same, so compare should also succeed. We can check whether, so we can first see what we have here to anticipate the result. It didn't work. Right, because this should be without p here again. Let's rerun it. Okay. Right, so this will also return true. We step over it, and then we return the value, and then we can print that we have found it. Okay, voila, found 5, data 1, 5, 2, and so on and so on. So this is how a hash table works. We also have exercised through a few memory allocation mistakes. So I think this should exemplify well enough that the C approach with using raw memory accesses and allocating your memory manually is very, very error prone, as I have demonstrated in a very convincing way. What our table is now still missing is the ability to remove something. And since the next, I think, 2 weeks there are no lectures because of the Easter holidays, I think it would be a good first more complicated homework for you to implement a remove function. So we have find in table, and the other one will be remove from table. It takes the table, it takes the hash function, it takes the compare function, it takes the key pointer, and it to do, or here let's say homework 1 of 2, and the other one will be homework 2 of 2. Homework 2 of 2 from there. Remove from table function. It should yeah, from the booklet. And there is a catch-22, being that we need to free the memory, and the idea would be that the main implementation should not do its own memory freeing. So we will not call it remove, but we'll call it take from table. So it should probably remove, probably unlink the entry identified by the key from the bucket, and turn the used tree on says as null. Okay, and the way it would be used is that, well, instead of find, we just let's say we want to remove say key from, how much is it? So 0, 1, 2, 3, 4, 5, 6. Key from 6 is 6. So remove from table. Sorry, take from table. And on success, if does, then you can free it. Because the idea is now that we might use heap alloc or some other function. We might have created an own heap and then wanted to allocate things from there. So the implementation of the table itself should be agnostic to the memory allocation as used by the elements themselves. It should not be agnostic with regard to its own memory allocation, so it has to manage its own bucket array. But other than that, it should not manipulate any other memory allocations. Especially given that this object's, for example, a key might be not a fixed size array, but it could be a dynamically allocated array, which then would need to be freed separately. So in this case, the using free would also fail. So this is how this works. You just take it out of the array. You can do something with it. You could actually even just take it from one tree and from one table, and then put it in another table. So there are this is quite a very versatile approach. Do we need something else? Not really. Though we could add a insert to table. We could add one more homework, which is only marginally more complex. Append table. So this we will then change to 1 of 3. But again, it's not super difficult. 3 of 3. Append. Insert. Tail of the bucket, so that it kind of is then more order maintaining than the other operation. Good. And as an optional, one more optional assignment, here, no, here, bonus homework optional. Check if a entry with the event key exists, and in that case to false instead of inserting it. Yeah, this way the list, the table will be a will have unique values. You will not be able to insert something with a key that has already been used. And in most scenarios, this is the desirable behavior. Alternatively, add a flag to alternatively. No, but this complicates things. No, we don't complicate things. So what we could do is, if we would allow the implementation here to handle the memory management of the elements themselves, then we could made it such that the thing would be able to replace the element. But replacing means we need to free the old one, and as we said earlier, for the return function, we don't want this functionality in this tree implementation. Okay, so I think this is it. We only have 2 minutes left, and we didn't have a break, so actually we are over time. I think these are reasonably easy assignments. As said, you have 4 weeks in total. You have 2 weeks now that there is nothing, then you have 1 week until there is a lecture, and then you have 1 more week to the over next lecture to do it. So 4 weeks of time in total, which would be enough. On one note about the next subject on the next lecture, that will be C++. So we will start with C++ and with creating some more complex objects. And once we know how those C++ stuff works, further down the line, we will create an implementation of a hash table and of the list, which is C++ based, so it will work differently. And this will very nicely showcase the differences between the C approach of doing things and the C++ approach. And probably by then the strategy will be that I will implement you the C++ version of a simple list, and the homework will be to implement a C++ version of the hash table. But that's in the far future from now. So have a nice Easter break, and if you have any questions, you can email me at any point in time. We will see each other in 3 weeks from now, if I am correct. And yeah, and that's it. Bye bye.